here we're going to look at what happens when we hook up a capacitor to an AC alternating current voltage source. We want to reason out what will the potential difference be like across the source and the capacitor, what will the current be like in this circuit, and what will the charge on the capacitor be like as time goes on. Now, according to Kirchhoff's loop law, we know that the sum of the potential differences in any loop has to always equal 0 at all times. Let's assume that our source is oscillating as a sine wave. And it's going to, of course, keep going as time goes on. And let's say that it had been going for a long time. And we're just going to see what the voltage is like at time 0 on this clock. So at time 0, we don't have any potential difference across the source. Let's draw that state over here on the left. If the bottom terminal is labeled as 0 volts, then the top terminal must be at 0 volts as well when we're at t equals 0. In order for Kirchhoff's loop law to be satisfied, though, we have to have the sum of the potential changes be 0 in the entire loop. So there's no way that there can be any potential difference across that capacitor at t equals 0. So the voltage on our capacitor is also 0 at that time. Now when we get to a new state, right here, we see that the voltage across the source is now 2 volts, and it's positive. So if this point is designated as 0, then this point will now be designated as 2 volts. So what must be the voltage across this capacitor in order for Kirchhoff's loop law to be satisfied? It must be that this point is also at 2 volts, and this point is at 0 volts. So the potential difference across the capacitor is actually going to follow the potential difference across the source. Now, what will the charge be like as time goes on? At t equals 0, when our capacitor has no potential difference across it, the charge on the plates will be 0 as well. This is because, according to the formula Q equals C times the voltage, the capacitance is just a constant. So it should be clear that when the capacitor voltage is 0, the charge on the plates is 0 as well. But here, when we do have a positive voltage across the capacitor, then we do have charge on the plates. And so what the charge is going to do is it's going to have the same shape that the voltage has. And it'll keep going. But what about the current? How do we rationalize what the current is like here? Well, it may be helpful to think about this as a river flowing into a reservoir. The flow rate of the water is the current. And at t equals 0, we see that the charge is 0. Q represents the charge stored on the plates of the capacitor, but it can also be thought of as an analogy as the amount of water that's stored in that reservoir. When the reservoir is empty, do we have to have current in order to start to fill it? The answer is yes. We need current to be flowing while the reservoir is filling up. But what happens when the reservoir becomes full? Well, at that point, we can stop the current. So I'm going to start the current up high when the charge is 0. And then I'm going to let the current go to 0 when the capacitor is full. Then the current is going to reverse direction and flow backward out of the reservoir. What this makes is a graph where current is at a high level before the charge is. And then current ceases when the capacitor becomes full. Now, current has to go in the negative direction in order to start to empty that capacitor. That's the idea here. When we have a capacitor in series with an AC source, we find that the current is 90 degrees out of phase with the voltage. And in fact, the current will lead voltage by 90 degrees, or pi over 2 as an angle. This is very different from when we have just a resistor in series with an AC source. When we had a resistor in series with an AC source, we saw that the current and the voltage were in phase. There was 0 degrees of difference between them. And when we saw the phasors, we saw that they traveled together at all times. They always pointed in the same direction at the same phase angle. Now what we're going to see is that our current is in a phase of 90 degrees when our voltage is in a phase of 0. So when we go to draw our phasors, whereas our voltage will point in one direction, starting at 0 degrees, our current at that time will be 90 degrees ahead. They'll both spin around the circle with the same angular frequency, but current will always be 90 degrees ahead. Now we also want to be able to give formulas for each of these curves which will predict the voltage and the current and the charge at different times. So for our source voltage, we can use V of t equals V max times sine of omega t. And that'll be our formula for the capacitor voltage as well. But when it comes to our current, we can use cosine. It's either that or we could use a phase shift as well if we want to write it in the form of sine. So if we want to write it in a different form but still get the same values, we can do that. We can write I max times the sine of omega t, and then we'll just shift it by pi over 2. And that'll be another way to express the current function. But we want to make sure that our current is leading our voltage by 90 degrees whenever we have just a source and a capacitor in series. For our charge, the formula can be Q of t equals Q max sine of omega t.